Section. Introduction. In this paper, we're exploring the potential of state space models, SSMs, which have been gaining popularity as an alternative to transformers due to their linear time inference, parallelizable training, and strong performance on tasks requiring long context. Specifically, we're looking at the Mamba model, which uses selective SSMs and a hardware-aware design to achieve impressive results. We propose that to fully harness the power of SSMs, they should be combined with a technique called mixture of experts, MoE, which is commonly used to scale up transformers. We introduce a new model, MoE-Mamba, which combines the Mamba model with a MoE layer. This model allows us to take advantage of the efficiency of both SSMs and MoE. We also demonstrate that MoEMamba behaves predictably when the number of experts changes. Our experiments show that MoEMamba requires 2.2 times fewer training steps to achieve the same performance as Mamba and shows potential improvements over Transformer and Transformer-MoE. These initial results suggest a promising research direction that could allow SSMs to scale up to tens of billions of parameters. SSMs are a type of architecture used for sequence modeling, originating from control theory. They can be seen as a combination of recurrent neural networks, RNNs, and convolutional neural networks, CNNs. Despite their potential benefits, there have been some issues with SSMs that have prevented them from becoming the leading architecture in language modeling. However, recent advancements have allowed deep SSMs to be scaled up to billions of parameters while maintaining computational efficiency and strong performance. The Mamba model, which is built on SSMs, offers linear time inference and an efficient training process through a hardware-aware design. It uses a work-efficient parallel scan to lessen the impact of the sequential nature of recurrence, and fuses GPU operations to remove the need to materialize the expanded state. Mamba also introduces a selection mechanism that controls how information propagates along the sequence dimension. This design choice allows the model to differentiate and retain essential information while filtering out the irrelevant. Mamba has shown strong performance across various domains, matching or exceeding the performance of established transformer models. MoE is a class of techniques that allows for a significant increase in the number of parameters of a model without greatly impacting the floating point operations per second, flops, required for the model's inference and training. MoE models benefit from sparse activation, meaning that for each token processed, only a subset of the model's parameters is used. We've followed this MoE design in our experiments. In terms of architecture, while Mamba differs significantly from the attention mechanism used in transformers, it retains the high-level, block-based structure of transformer models. In our MoEMamba model, every other Mamba layer is replaced with a MoE feed-forward layer. This design allows for the efficient integration of the whole context of the sequence into an internal representation by the Mamba layer, and conditional processing by a MoE layer that can apply the most relevant expert for each token. Section Summary. State space models, SSMs, have gained attention as an alternative to transformers due to their linear time inference and parallelizable training. Mamba, a selective SSM with hardware-aware design, shows promise as an alternative to the attention-based transformer architecture. To scale up SSMs, we propose combining them with mixture of experts, MoE, techniques, which have been successful in scaling transformers. Our model, MoEMamba, achieves efficiency gains and requires fewer training steps compared to Mamba, showing potential for scaling SSMs to tens of billions of parameters. Section. Alternative designs. We've conducted a variety of experiments, not only focusing on the combination of Mamba and MoE, but also exploring modifications to the original block design to incorporate conditional computation. We believe this line of research will be crucial in future efforts to enhance the Mamba architecture. More details about these experiments can be found in the appendix section. In our training setup, we compared 5 different configurations: the standard transformer, Mamba, Mamba MLP, MoE, and MoEMamba. In most transformers, the feed-forward layer has about 8 times the square of the model dimension parameters, while Mamba layers are smaller, roughly 6 times the square of the model dimension. This makes 2 Mamba layers equivalent to the combined parameter count of a feed-forward layer and an attention mechanism. To maintain a similar number of active parameters per token in Mamba and our model, we reduced the size of each expert feed-forward layer to 6 times the square of the model dimension. Excluding the embedding and unembedding layers, all models access around 26 million parameters per token. We trained the models on approximately 6.5 billion tokens and 100,000 steps, using the English C4 dataset for the task of next token prediction. The text was tokenized using the GPT-2 tokenizer. The learning rate was tuned for the standard Mamba model and reused for all other training runs. For a complete list of hyperparameters, refer to table. The results of our training are presented in table. The MoEMamba model showed a significant improvement over the standard Mamba model, achieving the same performance as the standard Mamba in just 46% of the training steps. We anticipate even better performance if the training procedure is optimized for MoEMamba. We also observed that Mamba MLP performs slightly worse than the standard Mamba. To evaluate whether Mamba scales well with an increasing number of experts, we compared different numbers of experts in our model. We also included Mamba and Mamba MLP for reference. The results, shown in figure and table, indicate that our approach scales well with the number of experts. If the number of experts is 8 or more, our model outperforms the standard Mamba. We achieved the best result with 32 experts. In terms of future work and limitations, we've only conducted experiments on models smaller than 1 billion parameters in this preliminary investigation. Given that MoE has allowed transformers to scale to unprecedented sizes, we're eager to see the impact of scaling on our proposed approaches. Our experiments show that combining the Mamba layer with a high-performing sparse MoE feed-forward layer results in a promising model. However, Mamba performs slightly better without the feed-forward layer in a dense setting. This suggests that integrating sparse computation within the Mamba layer itself could yield even better results while maintaining a simple, homogeneous architecture. We're also interested in exploring different types of MoE in MoEMamba. While our design is based on the commonly used switch, numerous other architectures have been proposed. These designs may not only perform better overall, but they might also be optimal with Mamba. Potential changes in this regard include expert choice routers, fully differentiable architectures, varying the number of experts and their granularity, and other modifications.